Thank you. Welcome to the nightmare session. How many of you had perfect data when you began your analysis, that had no missing values, that had no duplicates? All right, that's what I thought. So that's going to be the topic of our presentation. We're going to talk about the dirty data, and we also going to demonstrate some cleanup methodologies using the data set, public data set that is that's using the Fitbit data from some group of people. So a little bit about us. Tanya is the Vice President of Model Governance and Review at JP Morgan. Myself is the Faculty of Analytics at Harrisburg University, and I'm also the Data Science Advisor at metadata.io, which is the account-based marketing startup. So Excel first came in as a Lotus 1, 2, 3 back in the 70s. IBM, well, I believe IBM was the first one who acquired the tool later on, acquired the company later on. However, still up to this day, according to Gartner, Excel is the most used, most popular BI tool in the world. So if you look at their Magic Quadrant, Microsoft is actually being at the very lead of all other tools. So the reality is that no matter how sophisticated is your BI tool, people will still convert it to Excel and work in Excel and then upload it back to your sophisticated tool for which you're paying a lot of money. So bottom line is that Excel is the most widely used analytical tool in the world. So if we're talking about data, dirty data, significant quantities are stored and passed around in the spreadsheet because, again, the adoption rate is very high. The analyses are also frequently performed without leaving Excel. And this can lead to very aggravating data quality issues. So when the data happens to be not as clean as you hoped, serious errors can occur, and you have to deal with these errors through the work cycle. Another statistics from the public research company, IDG estimates that about 60% of the data science workflow is occupied by the data cleanup. So eventually, majority of the data science is eventually what they're doing data engineering, essentially. Some of the common types of dirty data are missing data, duplicates, outliers, multiple comma separated or not, values crunched into the same cell, and column headers as values or variable names, not variable names. So there are a couple of ways of handling dirty data. One would be the database level manual cleanup, which is non-scalable and inefficient. The other one is the application level, the recommended way. Basically, you're trying to hack off the problems at their inception. Hadley Wickham is the British statistician who developed, in 2014, developed and published the article on with the concepts of tidy data. So the main concepts are the observations should be as rows, variables should be as columns, and you have to have one observational unit per table, which is actually relates very closely to the normalization concept. So to demonstrate how to, to demonstrate some methodologies of data cleanup, we have a data set, a publicly available Fitbit data set containing about records on about 33 customers with the minute-by-minute records on steps and intensities, as well as daily distances traveled. And data quality issues were manually introduced by us for the purposes of this demonstration, with the objective to provide a simple example that illustrates how data quality issues may affect the results of the analysis, as well as to estimate the more tactical objective is to estimate the customer's height based on the average stride length and see whether the results belong at the expected ranges. So the tools we used were obviously Excel, Python 3.5, and Jupyter. So initial data that we had consisted of three data sets: the minute steps, minute intensities, and daily distances. The minute steps is pretty self-explanatory. It lists the steps the observed unit made per minute. The minute intensities estimates, so the intensity is the measure that estimates how intense was the step. So in other words, if I'm walking from here to the next chair, the intensity would be 0. And then it goes up with 3 being very intense, maybe running or jumping. Daily distances has three variables: light active distance, moderately active distance, and very active distance, which come up to the total distance walked throughout the day. So the quick and dirty height calculation, I probably should use this slide. So the first step we've done, we merged this two data sets. We've merged minute intensities with the steps, just because the measures, the variables are very similar, and we were able to merge them by the IDs. The reason we did that was we wanted to have the ability to filter through the intensity, which we eliminated all observations where intensity was 0. Next step, we merged the resulting data set with the daily distances. And finally, we arrived at our model, which is down below. So the reason we didn't go into sophisticated calculations, because again, the purpose of this demonstration is the data cleanup and not the actual calculation. So what we did, essentially we're using the distance divided by number of steps, multiplied by the coefficient. The coefficient is actually something that was looked up on the web. I believe Fitbit has this coefficient posted, and finally the last line is the formatting of the output. Once we ran the model, some of the height calculated by the formula were clear, clear outliers. There was a 3 feet tall person, there was an 8 feet 3 person, 13 feet, and 1.5 feet. So that's clearly erroneous data. So to elaborate on how we cleaned it up, I'll pass it to my peer.
Hi everyone. So I'm going to explain how I cleaned up the data, but before I do so, I'm going back again to here. So we chose this little simple model to send this message to everyone that cleaning data is super, super important. Your model can be, it doesn't have to be as simple as we chose. It could be very sophisticated, very interesting, and very valid model. But if you feed your valid model dirty data, you're not going to get anything meaningful in the outcome. And the reason we chose this example is to illustrate that you can visually see how your observations are really off. You can visually see that a person cannot be 13 feet high. It just doesn't happen. So here you can see it. In most practical instances, what happens is you wouldn't see this visually. Like when you look at your results, you won't be able to tell that you had some problems in your data that caused this, because you wouldn't, everything is generally more nuanced than this. So this is just to send a message that this is very important. And I've been working at JP Morgan I've been validating models for almost 4 years, and this aspect has been overlooked continuously, and this message doesn't get across. People model, but people don't look at the data. So with that said, I'm going to move on into cleaning up and see what we can do. First and foremost is what you do with your data is you actually need to look at it. This is a few simple ways how you look at it in Pandas. However, of course, going more sophisticated with data visualizations and other methods is important. Here we only focus on the very simple observations. So there are couple of simple things you can use. There's an info function in Pandas and describe. They do different things. So describe gives you like basic statistics on the integers and floats, and info gives you information about your variables, what kind of data types they are, how many observations there are. So first thing first, let's see what we can see from this data set. And I hope this, yeah, there's a pointer. No, it doesn't work. So they describes. First of all, you can see that you saw that the minute steps and intensities, they look very similar in terms of data, right? You have ID, you have activity minutes, and then you have your variable, your value, steps or intensity. Here, when you look at describe, they look different. What happened? So one thing you can notice is the ID is a numerical value. It's an integer for intensities, but it's not an integer for the steps, and you can see it in the info as well. You have a data type object. So this is something to be worried about. There's something wrong in your data that makes one integer and another not. Another thing you can see is that most of the values are 0, so even 75th percentile is 0 for both. And you can also see that for the steps, the maximum value is sort of off. It says that a person walked 500 steps per minute. That's too much. So you also have outliers in this data. Other observations, you can see that there are some null values in the steps, in the steps table, because if you look in the counts in the info slide, the counts are off. So there are null values, and another check is the number of customer IDs in the steps and intensities are different. One is 33 and another is 36, which also kind of asks you why is it happening? Why are they not matching together? So you can see a lot by just doing this very simple thing. And this is kind of a message, always do it before you proceed. So those are just the observations I just mentioned. We have a different number of records. We have a lot of zeros. We have nulls for sure. We have different number of unique user IDs. Some object data types for something that shouldn't be, like, well, ID doesn't have to be an integer, but we know when one is integer, one is not. And the maximum number of steps per minute is 500, which is also too many. One file we haven't looked yet, it's daily distances. One thing we can see is that the number of unique IDs for this one actually matches the intensities. So 33 seems to be the right number, not 36. And we can also see that there's 4 different types of distances here, which may or may not correspond to intensities. There's a sedentary active distance, and then the light and moderate and very active. We will assume that they do correspond to the intensity, so we only look at the distances that are more active. So having those observations in mind, let's go and actually clean the data set. So first thing first, look at the IDs and see what may be wrong with them. So this minute steps is where the problem is. And if you look at them, you can actually see that there are some weird things start happening on the second column, where you have some weird strings with some additional characters appearing. And that's what's causing the problem. So we need to clean this up. And another thing you can see is that the minute intensities has way too many records, and if you try dropping duplicates, basically you can see how you actually have whole duplicate rows in this data frame. So if you start merging, that's the first thing we did in the dirty calculation before. This is if you start looking carefully how many records you have when you start merging, so you can see that it changes. You have 3 different numbers. You have number of records in minute steps, number of records in minute intensities, and the number of records in the merge. They're not the same, which is not what you should be expecting. Like, ideally they should match one by one together. So to clean it up, we first convert the IDs to integers. We just clean up all the dirty characters. So this is what the first function is doing. And the second thing we're doing is we are just dropping duplicates in the minute intensities, because they're just there. We know those records are fully duplicates of each other. And once we do that, you can see that the merging works well. There's no problem anymore. So now we have records matching 1-to-1. The next problem is slightly more complicated. So once you figure out the duplicates and things start matching together, nulls and outliers are the harder problem because you actually have to conceptually understand what they mean. In this particular instance, we kind of won't go a mile to do that, but in general, you need to understand why your nulls are occurring. In our case, we introduce them, but in your case, it's probably something else. And why are outliers occurring? What do you mean by outlier? Why do you think this is outlier and something else is not? So it's usually a very tricky question, but here we just given, again, one simple example. So missing values. Usually missing values are treated using imputations. There are multiple kinds. There are simple single imputations, or multiple imputations, which basically ask you impute it multiple times, do your analysis, and then kind of take an average or look at the distribution of your possible outcomes. But generally speaking, the idea is you're trying to predict what you missed. So you can do the same with outliers. You can either just exclude them, or you can kind of impute them as well. Because if you think your outlier occurred because, I don't know, the device that has been collecting data is broken, or something happened that is not something technical, then theoretically you may want to replace it with the imputed value. So the most typical single imputation are mean substitution. You can substitute just put mean value instead of a missing record. This is a valid method if you only have very few of them and you don't think it's going to affect your results significantly. But sometimes the mean can do kind of a bad job for you. For example, if you are trying to actually estimate the average number of records, you are losing your noise, in a sense, by replacing things by the mean. Another method is interpolation, which is usually meaningful if you have time series data, what we do in this case. We have per minute information, so we can use interpolation to impute the values. There are also some people just delete the data. It's sometimes a valid method when you delete the records. In our case, it's not going to work because we have to match our information with the daily distances. And the daily distances are daily distance. So if you throw some of the minutes from the intensities or steps, then they're not going to match conceptually to the daily distance. So we can't throw away records, but there are situations in which this is a valid method to proceed. As long as you don't throw away too much data, it may be okay. Another way of imputation is to replace with a random value. So the one is hot DAC is you take kind of values that you have in your data set and just replace with a random one of the existing values. The cold DAC is a similar method using a data set that is different from yours. And more sophisticated method, you can use a regression to impute the values. But the regression, again, you need to be very careful about it because you are, again, replacing, so to speak, with an average per category in some sense in the regression. So you are losing some of the noise in the regression. So just a quick note that the multiple imputation, out of those methods, the hot DAC or cold DAC would be kind of a suitable for multiple regression, where you can try different values. You can randomly select one and then randomly select another and another and see how it works. It's often a recommended method because you often don't have enough data, or you have you need to impute too many values or things like that. So in some instances, it actually gives you kind of a better estimate in the end. So there are advantages. It's relatively flexible. It's easy to implement, and it gives you sort of a better view. The disadvantages are sometimes it's not giving you any additional benefit. So in our example, it turns out that with the methods we tried, it doesn't give you additional benefit. So it is more computationally intensive, but in this case, it wouldn't give you anything, but you definitely should try it and see if that works in your case. So back to example. So this is just a plot of the step distributions per intensity, what you can observe is for intensity 1, the distribution kind of goes down sort of exponentially. I don't know, but there's a clear kind of stepping down, and then the intensity 2 and 3 look more like normals. So the scale is counts, and then those histograms of the number of steps. So just to visually, we have most of the intensities are 1. I mean, aside from 0 in this distribution, and so that's why we kind of, when we did the model, we chose this sort of average stride lengths between running and walking. So because we don't have too many observations in the intensity 2 and 3 to kind of model them separately. So now let's impute. So this one simply makes a single imputation using the mean. We compute mean per customer, not mean per, per the whole thing, because we would expect that the mean number of steps would depend on the person who is wearing Fitbit. Some people run more, some people less. So we compute that per customer, and then we just simply replace all the nulls and all the rows where you have 500 as a outlier. Another one is interpolation. We simply interpolate here with the previous value. So basically, if you walked, 30 steps in a given minute, and then they have a missing value in the next minute, write 30 until you find a non-missing value. So it's like, there are many different kinds of interpolation. You can also use the average between the two, so you can specify in the interpolate, and here you can specify what kind of interpolation you're looking for. And another one we used was the hot deck is the random choice. So we basically took the distribution of existing values for the steps and plugged it in. And for that, we used the transform method for the Pandas, which allows you to sort of transform your data series into something else. And here we kept the same value if it existed, and if not, then we just drew randomly from the same customer. So now it's just rewriting our model, so to speak, into a function. So once again, we already merged the two files, so now we only need to filter out for intensity bigger than 0, sum things up, take the distances which are not sitting down, but actually from some activity of the customer, sum things up, and apply exactly the same model as before, and format the height so that we can actually better visualize and understand it. And once we apply it to every single of those imputation values, this is the result. So the result, we only filtered out the situations where the dirty calculation was different from the original calculation. I took out all the other customers so that we can see. Well, one thing to notice is in our old graph back here, we only noticed 4 problems, right? 4 values really stood out. In this graph, we actually see 5. So there was one that we missed because this one was 6.4, which is sort of, acceptable height. You can't say it's off. But this one also had a problem. We couldn't see it visually by looking at the values, but it was there. Yeah.
What's the column height interpolate?
Oh, those are depending on imputation. So height, mean, height, interpolate, and height distribution were the 3 imputations that we used. Height, mean is the imputation we used with the mean value. Interpolate is the interpolate value, and the distribution is the when we did the hot deck by selecting a random choice. Yes?
I wanted to ask again. So height mean, you said you can use replacement with the mean value.
Yeah.
Only if those aberrant values are few. But how do I decide few? Is it by percentage? Is it...
Well, I mean, it's a difficult decision every time. Percentage usually works, but it's good to look at the distribution of your values and see whether mean is actually a meaningful parameter. So what happens in real life, here's just one example. You can try all those sort of things and kind of see how it works. But in production, you have to decide. If you actually imputing data in production in the process, you have to decide which one you use. So you need to study it and see whether mean is appropriate. It depends on what kind of how distribution looks like, whether this is gonna affect your downstream results if you start modeling with this data. So it's a tricky question. A lot of people use the mean, but it's not necessarily the best choice. A lot of people also use interpolate, but you can see in this example that it's not really performing as well as some other methods. Like, for example, the 1.5 problem, it didn't fix it, the interpolation. So there's something, I mean, it's not necessarily a bad method altogether, but you need to be careful when deciding which one to use. And in this, again, in this example, the distribution worked out the best. Part of the reason is that because when I introduced those problems in the data set, I did them uniformly at random. I randomly replaced values with nulls, and I randomly added the outliers. That's why when you use a distribution to replace them, you actually kind of get things back. Not perfectly, but good enough. And other methods are not as good because they are doing something different. But so the imputation that you choose really depends on the cause of why you're having the null values, why you're having the outliers. So asking those whys with your data set is very important, and it really varies case to case, but this is something that I think when you do any analysis is something that you should ask. This is before modeling, but it's so crucial to the results that your model can possibly obtain. So we'll send us a bad data set, and we'll figure it out, I hope.
And with that, we will take questions.
My question is, when you say it's outliers, are you referring to a suspicious data point? I am a little confused because when I trained in statistics, it was my missions to determine if it's an unusual data point was an outliers, or actually it was an unusual observation, but it's still a valid observation. So a data could have these kind of data points that it wave, are not within the group, but are not necessarily outliers. So I needed to run the test to find out if that indeed was an outliers, and if it was an outliers, I can safely remove it, and it would not affect my models. But if it was an outliers, it was not. If it was not, then I have to leave it in there. So in fact, an outlier has to be determined. You cannot define it a priori. And I wonder if when you mention outliers, you are thinking the same way, or I'm confused. It's only a noise.
Yeah, I fully agree with you. It really depends. In our case, I just specifically made it 500 steps per minute, which is practically humanly impossible to achieve. So that is clearly there's something wrong with the data, and not with it doesn't sound like a valid value. But if the value was, say, 200, then you'd say, yeah, if you run, you may get 200 steps per minute. There's nothing wrong with it. So you would start thinking, oh, is it a real outlier, or it's just because somebody's really fast and they just step a lot? So yes, there's absolutely, this question is very important. And another question is, if you are planning to apply a model after that, it's important how your model is gonna treat this value. Yes. If the model is capable of kind of working around it, so to speak, or treating them in the right way, you can keep them. But in some instances, models are not very sensitive to outliers. Then you might have to think about it harder, like regression is relatively sensitive and so on. Yeah.
So as we saw kind of all the impossible cases from dirty and clean, you have the overall population distribution before and after. Did it affect that?
Overall population distribution for number of steps?
For trying to
Yeah.
get the height. So when dirty, you showed a whole bunch of,
Mhm.
there's no such thing as a 13-foot tall person, but you have the overall height distribution for the populations before dirty and after.
Yeah, so we only had 33 records. So the distribution was, as we show, this is only 33 customers. So this is, I mean, you can plot it as distribution, but that's all we have. And for the ones that we corrected those 4 squares, and one of this, I believe this record as well, that was actually off, but you couldn't see it in this table. And once again, in this particular instance, we actually introduced them per customer. That's why they're so clearly per customer. But in regular life, you would probably it will probably affect all the records to some extent.
Maybe one last question. Not so let's thank the speakers again then. Thank you.